So now we're going to do a couple example problems involving these equilibrium expressions that we've been discussing. So here we have hydrogen gas plus fluorine gas in equilibrium with 2HF. The Kc at 298 K is 1.15 times 10 to the third. And we are asked to calculate the equilibrium concentrations of all species, assuming 3 moles of each component was added to a 1.5 liter flask. Okay, so let's first calculate our initial concentration. If we have 3 moles per 1.5 liters. So if we divide 3 by 1.5, we're going to have a concentration of 2.00 molar for each species. So that means 2.00 molar for H2, for F2, and for HF. So if we set up our Q expression is going to be products, which is the concentration of HF squared, divided by the concentration of the reactants. So this is going to be 2.00 squared divided by 2.00 to the first power times 2.00 also to the first power. So our Q is going to equal 1.00. So in this case, Q is less than the Kc, which tells us that the equilibrium needs to shift over to the right to reach equilibrium. So one of the things that we can do here in order to analyze our reactions at equilibrium is set something up called an ice table. And an ice table is used to look at the initial, the change, and the equilibrium concentrations of everything present. We have 2.00 moles in terms of the concentrations of all species initially. This equilibrium is going to shift to the right. That means the concentration of HF is going to increase, and the concentration of H2 and F2 are going to decrease. The change in concentration is going to be dictated by the stoichiometry of the balanced chemical equation. So for every X moles of H2 that decreases, there's going to be X moles of F2 that's going to decrease, and there's going to be 2 times as many moles that will increase for HF. So we do this by putting a negative sign in terms of the change that happens for the hydrogen and the fluorine, and plus 2x and a positive sign for the increase of the concentration of the HF. So at equilibrium, that means our concentration is going to be 2.00 minus x, 2.00 minus x for both of the reactants, and 2.00 plus 2x in terms of the equilibrium concentration of the product. So then we can set up our Kc expression, which is going to be the concentration of HF, that quantity squared, and this, remember, is an equilibrium concentration, the concentration of H2 at equilibrium times the concentration of F2 at equilibrium. And in the future, I'm probably not going to include the equilibrium here because that's going to be implied by knowing that we have a K expression. So if we plug these values in, we get 2.00 plus 2x, that quantity squared, divided by 2.00 minus x, that quantity also squared, because it's going to be 2.00 minus x times 2.00 minus x. That is going to equal 1.15 times 10 to the third. And that's our Kc that was given in the problem here. So now what's going to happen is we're going to have to multiply out each of these expressions. So we're kind of going to have to go back in a little bit of time here and look at algebra class, because to evaluate this expression we would have 1.15 times 10 to the third times 2.00 minus x, that quantity squared, and that's going to equal 2.00 plus 2x, that quantity squared. So if we multiply this out, we have 1.15 times 10 to the third times times 4 minus 4x plus x squared. That's going to equal 4 plus 4x plus x squared. So we have to distribute everything through here in order to figure out, to solve for this quadratic and figure out how to solve this particular problem. Okay? And now that I'm looking at my notes here, I'm seeing this should actually be 1.15 times 10 to the second. So I'm going to fix that everywhere that I have 1.15 times 10 to the third here. Sorry about that, but that's going to cause the numbers to work out here a little bit more. So if we have 1.15 times 10 to the second times the quantity 4 minus 4x plus x squared equals 4 plus 4x plus x squared. So if we distribute all of this out, we're going to get 460 minus 460x plus 115x squared, and we bring everything back over here to the left side of the equation, minus 4 minus 4x minus x squared is going to equal 0. If we combine like terms, we're going to have 114x squared minus 464x plus 456 is going to equal 0. And if we apply the quadratic equation, which I'm not going to go through the details here, we're going to find that x is equal to 1.53 molar. Okay, remember what we're trying to solve for here. We're trying to solve for x, which is going to correlate back to the change in concentration that we used in our ice table right here. Okay? We're asked to determine the equilibrium concentration of each species. So the concentration of H2 at equilibrium is going to be 2.00 minus x. The concentration of F2 at equilibrium is also going to be 2.00 minus x. And the concentration of HF at equilibrium is going to be 2.00 plus 2x. We have solved for x right here. So our concentration of H2 is going to equal 2.00 minus 1.53, or 0.47 molar. Our concentration of F2 is going to be the same. And our concentration of HF is 2.00 plus 2x, or 2.00 plus 2 times 1.53, which is going to give us 5.06 molar. And these right here are going to be the equilibrium concentrations of all the species present. So when we look at a particular problem like this, to kind of recap everything, we need to first determine the initial concentrations of all the species present. Then we have to compare Q and K to figure out which direction our equilibrium will shift. We set up an initial change equilibrium concentration table, or an ICE table, for the particular reaction. We then can solve for the equilibrium concentrations in terms of x, or how they would change. We plug those in to our K expression. More than likely, we'll have to use some type of quadratic equation to solve these particular equations. So we plug that in, do the algebra, use the quadratic equation, solve for x, then go back to the equilibrium concentrations in the ICE table, use the x that you've calculated, and then plug that back in for our equilibrium concentrations, which are listed right down here as 0.47 for hydrogen and fluorine and 5.06 for the HF.